Hola, buenas tardes. Es un gran placer presentarles a Dr. Nathaniel Butler de Arizona State University. Nat realizó su licenciatura en Princeton y luego el doctorado en MIT, trabajando con datos de GT2. Después de eso, realizó una estancia bastante larga en Berkeley, primero con una beca Towns y luego con una beca Einstein, trabajando más generalmente en astronomía del dominio de tiempo. Y luego, en 2011, se cambió a Arizona State University, donde es profesor. Y hoy nos va a hablar del título Chasing Explosive Transients.
Use this one. See if it works. Hello. I appreciate the invite and the chance to speak. Thanks for the intro too, Alan. So I want to talk about chasing explosive transients. And specifically, I wanted to talk about gamma ray bursts and their connection to gravitational waves and gravitational wave detections. And I want to do this because I'm here to work with the groups here to do more of this chasing in the next year with facilities at San Pedro. And because I'd also like to share some of the work I'm doing on software with folks here and hope that you can use some of the reduction capabilities that I'm developing, hopefully to get more out of instruments like RATIR or other things at San Pedro. Okay. Feel free to interrupt me at any point. Let me start with this slide. This is a really cute summary of the LIGO detections in the last few years. What it shows is distance versus, well, distance in two different units, light years, megaparsecs. And so the key thing here is that really distant sources from the Earth are over here, and really nearby sources from the Earth right there are here. And most of what LIGO was finding were these very distant, gigaparsecs away, binary black hole systems, and really bizarre systems with sort of 32 and 19 solar mass black holes, things that are surprising to exist at all. Okay, and that was a bit of a shock, I think, to groups like ours, which at ASU also involved people here at UNAM. That we weren't finding more of what we expected, which were the neutron star mergers, like this event that happened in August of last year. That finally happened in August and was the sort of biggest news of that year, right? This really exciting binary neutron star event. Okay. So I'll talk about this, and what I want to kind of focus on is thinking about where we go from here. So this event was only one of a number. It's not exactly clear at all how many more we expect to see. And now that all these gravitational events are going public, it's not just private groups doing them. How do we coordinate to effectively chase and find more of these events? And how likely are we to do that? Okay. That's my overall thrust here. So let's look back at that event back in August of 2017. Okay, it was this is a little cartoon of what we think happened. So it was an in spiral of two neutron stars, and as the stars are coming together, the gravitational signal is ringing up, and it kind of chirps when the merger happens, and you're left with either a bigger neutron star or a black hole as a result of that collision. Okay, and so this was a huge discovery. Obviously, the detection of this event is a decades-long in the making effort to build these massive 2-kilometer-long laser beams that are controlled with exquisite precision. It took generations of scientists and engineers to make that happen. It's a very hard game. But the game that we work on, which is the ground-based follow-up to find the electromagnetic counterparts, is also a very, very hard game. Okay, and I want to focus a little more on that. And this was the big result from August, that some folks pointed their telescopes down in Chile at a galaxy which was in the air region, and lo and behold, there was a new source right there off to the corner, which turned out to be the optical counterpart to this gravitational wave. burst. Okay. And our group, working with people here, led by Nora Troya at Goddard, followed this up in the X-rays and determined some other really interesting things about this source. As I'll talk about, it looked like the gamma ray burst that was associated with this event wasn't pointed toward us, it was pointed away from us. This is very peculiar and also very challenging to allow us to think about what future rates might be. In any case, we followed this up for weeks, months. It's still being observed with Chandra, and I think it's finally not detected with HST. But it led to the 2017 Nobel Prize in Physics. So a lot of the fun around this event was to try to stay quiet. We all know it was happening. We were all writing our papers, but we couldn't talk about it until after the Nobel Prize came out. And I commend everyone here and elsewhere for keeping the lid on those results. Okay. And it was great stuff. We learned a whole lot of stuff about the universe from this one detection. I want to focus a little more on what we learned about gamma ray bursts and really where we go from here. Okay. Let me set this up with this plot. This is the Earth, and what it shows you are a few different gravitational wave error regions produced by LIGO. Okay? They're like these bananas. This was the really nice one, really small back in August, but typically they were nothing like that. They were these giant regions that span across the globe. And so to follow those from the ground, we had to point a telescope over many, many parts of the sky and sort through many, many potential sources to find the interesting optical counterpart. Okay. And this is a plot of what the gamma ray data look like. So this is all, I think, really amazing. There's the LIGO data. So it's increasing, this is time. It's increasing in frequency, so it's sort of chirping up here. And then at the time of the merger, which is shown here in black, there's not much happening in gamma rays, but about a second later, there's a very short pulse of gamma rays seen by the Fermi and the integral satellites. Okay. It's, I think, just amazing to think about. You know, these two signals are less than 2 seconds apart, yet they propagated through 100 million light years of universe. So this is just phenomenal that you still have that kind of coherence. The gravitational waves travel at that close a speed to the speed of light. It's just kind of phenomenal. For years, we didn't know exactly that would be true. Do we have to search for gamma ray bursts within an hour of a gravitational wave signal at the same time? Well, here they're just practically simultaneous. So that's really wonderful from the standpoint of identifying and trusting in the optical counterpart. Yeah.
Was that expected?
Well, it's predicted. Sure, it's predicted that gravitational waves should travel at the speed of light, but you know, there's a big distance. Does it actually happen? The physics are super messy. So does the collapse of the object and then the eventual production of this gamma ray burst, does that happen really simultaneously, or does there have to be some production of a accretion disk? And you know, so it's messy, right? But the fact that it was this close in time is just, I think, phenomenal. And it actually allows you to say, you know, the gravitational waves travel very close to the speed of light. Okay, so that was, you know, that was great. That was our first electromagnetic counterpart to a gravitational wave detection. Okay. I want to sort of say what happens in the optical a little more. So this is a more typical error region there. It's not just in one part of the sky. It can cover the part of the sky under the ground, right? These can be really large error regions. So when one of these detections goes off, it's kind of a worldwide effort to go out and chase possible variable sources in that region. Okay, so the typical error region is a few hundred square degrees. It can be 1,000 square degrees. Sort of best case, maybe 100 square degrees, but they're very, very large. So you're talking about hundreds of thousands of catalog sources, thousands of bright galaxies that you might have to look around, many, many potential things to look at. The problem is that telescopes don't typically have fields of view like that image right there, right? Telescopes typically have pretty narrow fields of view. And so what you have to do is many pointings over a reasonable period of time. These things are going to fade on day or a couple of day time scales. So you have to sort of be able to point at this region in the course of a night. Okay, so there's really a couple strategies. I'm going to go into these two strategies, and then I'll relate that back to what we're trying to do at San Pedro. So there's a large telescope strategy, sort of narrow field of view strategy, where you go and you just look at the known bright galaxies. So LIGO is only sensitive to a volume of 100 or 200 megaparsecs. We know most of the galaxies in that volume, and we can just point at those positions. Okay? That is a 50-50 game. We can't go after every galaxy, but we can cut the luminosity function at 50%, and we can go after the brightest half in a way that allows us to look at everything in a night. Okay? So it's not perfect, but it's a strategy that allows you to use a big telescope to go after faint sources. You can couple that with another strategy, which is the small telescope strategy. So small telescopes can have much larger fields of view, so you can point them at the entire region and hope to image it and capture images of the entire banana there. But the obvious drawback to small telescopes is less sensitivity, right? So you can't go as deep. You have an ability to go after the whole thing, but to a very shallow depth. Okay, so it's sort of a multi-pronged approach where we're trying to rapidly go after these very large regions, pick off some of the most likely positions, and try to do something okay with the rest. Okay. Yeah.
So how long does it take when you know that there is a detection in LIGO and they emit the alert to the telescope?
Yeah, so it's a learning process for sure for them. So in principle, it can be very fast. The event in August was really interesting because they had I'm not sure exactly what the issue was, but the gamma ray detection came out first, and their detection didn't come out until they sort of knew something was interesting there, and they looked at the data from Virgo in Italy, and it took something like an hour, half an hour to an hour. Okay, that's fast, but compared to what I'm used to, that's ridiculously slow. So I'm used to this gamma ray burst game where you get your detections in seconds. Okay, but here it's more relaxed than that. It's hours, but you have these large error regions. That's the challenge, right? Yeah. Okay, so how do we chase these events? And this goes right to your question. So we're basically using the same kind of gear that we had from gamma ray burst land. Okay, so gamma ray bursts work like this. They're detected in space. And then the satellites that do this radio the signal to the ground. And the ground, which is aggregated at a thing called the GCN at Goddard, sends those signals out to various robotic telescopes or people with cell phones, anyone with an observatory in the ground. Okay, and this happens within a few seconds. And the way the LIGO process worked is they used the same GCN network, but with the detection coming from their facilities on the Earth. Right? But it's the same network, the same capability set that allows people that have been chasing gamma ray bursts for years to tap into this network and to chase gravitational waves in the same way. Okay? Let me just say a brief word about what gamma ray bursts are, because I want to connect those back to the gravitational wave sources. This is one of the first gamma ray bursts. You can see on the left is a map in galactic coordinates of the sky. If you had gamma ray eyes, the gamma ray sky. So what you see is the plane of the galaxy there. And here you see a source, which for a few seconds is getting very bright, and it's brighter than everything else in the gamma ray sky, but only for about 5 seconds. And this is what the time history of that event looks like. Okay? So kind of a silly but obvious name, gamma ray burst. A very bright explosion in gamma rays. And it lasts this very short period of time. Right? So that's what a gamma ray burst is. We've known about them since the 60s. Obviously, we know a whole lot now about what they are. We think the bulk of them are due to the collapse of massive stars, and we've been working on the physics and all sorts of fun stuff. There's one bit of phenomenology that's important here, and this is the fact that gamma ray bursts seem to come in 2 approximate classes based on their durations. So this is a famous plot that's been circulated for many, many years. This is a version that was updated in the 90s. What you see is if you measure duration, this is a log axis, there's a dominant class that has durations typically 10 to, say, 100 seconds. And there's a subdominant class here, which has duration shorter than about a second. Okay, and sometimes these are called long and short duration gamma ray bursts. You can see from the plot that it's not a clean distinction. Right? The 2 populations clearly overlap. Right? You can't sort of very trivially separate the 2. But in the course of the 2000s and through the Swift era, there's been a lot of follow-up on bursts in this class, the red class, and we've very clearly established that those are due or correspond to the deaths of massive stars. Okay, the nearby events, we can actually measure supernova spectra. We can associate those with supernova explosions. The bulk of events, we can find them in their host galaxies, and they tend to sit right where the star formation is happening. Okay, so they're associated with a young stellar population. There's not a whole lot more known about this class. We followed up to date about a dozen short duration gamma ray bursts real well. They don't tend to be in star-forming regions of galaxy. They tend to be in a range of different types of galaxies. Sometimes they can be outside of their galaxies. They sort of behave more like type 1a supernovae. Okay? And so there's been a suspicion for many, many years, for decades really, that this class could be due to mergers in very short time scales, mergers of compact objects, whereas the red class is the things associated with massive stellar death, type 1 BC supernovae. Okay? So that's been around for a long time. The only way you could really prove that, and probably the main way you could do it, is to find gravitational waves associated with one of these short duration gamma ray bursts. Okay, so you could actually find the gravitational waves, model those so accurately that you measure the masses of the two objects that are in spiraling and merging, and even the end product, and show thereby that this was in fact a merger of compact objects. Okay, so from the gamma ray burst end of things, we're very excited about gravitational waves because it allows us to figure out what are the progenitors. Instead of, yeah. So yeah, kind of analogous. Something that's maybe existed as long as the progenitor of a 1a supernovae, but you have two compact objects there. Yeah. Okay. And so that's been the kind of game for us, and that's been one of the most exciting things to look at based on this August of last year event. Does it confirm this picture that short duration gamma ray bursts are due to mergers, or is there still more interesting stuff to understand? And what do we really need to work out to answer those questions? Okay. So I want to put up a little cartoon about what we think gamma ray bursts are. Okay, there's a part of this plot to the left here that we'll call the central engine or the progenitor. There's a lot of mystery about exactly what that is, but massive star, some kind of very compact object, black holes or neutron stars. Somehow, this thing collapses and generates an explosion whereby a jet of gamma rays is released along some axis, perhaps the axis perpendicular to the rotation. Okay, and exactly how this happens isn't terribly clear. Okay, but we do know some basic things about what happens after that. So there's a gamma ray burst. Excuse me, my laser isn't working quite well, but the thing in the middle, the gamma ray burst, that happens because shells of different velocities are ejected and they self-interact. They kind of bump into each other. So the idea is that's what we call internal shocks. Very fast-moving, highly relativistic material produces synchrotron radiation. There must be magnetic fields present here, and that emits in gamma rays. Okay, that's lasting maybe 10 seconds, carries a typical energy about 1% of the rest mass of the sun, so tremendously energetic. And then on time scales of days to weeks, the outflowing material hits the circumburst medium and starts to shock up the ISM, and you get what's called the external shock. And that is something we can measure for quite a long time. Okay? A key thing to notice here is this yellow region, which I've called the jet. So the radiation doesn't come out isotropically, it comes out in a jet. And you only see that gamma ray burst if you happen to be sitting and looking down the mouth of that jet, right? So a really key thing here in this whole field is to understand how and perhaps why GRBs are jetted, to measure that, to understand both the physics of gamma ray bursts, but also the rates, the anticipated rates of progenitors. So the number of gamma bursts you don't see is really important to understand whether these things are due to massive stellar evolution. In the case of the compact objects, how many compact objects would need to be produced to make the gamma ray bursts? Or turning it around, how many LIGO events do we expect to see based on our understanding of gamma ray bursts? Okay, so this question of jetting is a really important question. And for some reason, we haven't totally solved this. Okay, so let's go back to this event. This was the LIGO event shown in optical and X-rays. What we saw in the left here was a fading new optical source, right? Ryan Foley used a telescope in Chile to find that. And our group contributed to the observation in the infrared particularly, and in the X-rays, the plot on the right from Nora Troya's paper. So this is all the afterglow, right? There was the pulse of gamma rays that happened. That was a gamma ray burst. This stuff is all being measured on timescales of days. This is ambient material being shocked up, okay? And it's lasted quite a long time. A really interesting thing about the X-rays is they weren't there initially, but they came about, they brightened after a period of a couple of days. So the interpretation based on the X-ray observations, the source right in the middle there, the thing called GW, was that the gamma ray burst probably wasn't pointed toward us. Okay, otherwise it would have been a bright X-ray source. And this is really interesting because we saw a gamma ray burst, right? We saw what looked like a short pulse of gamma rays a couple seconds after this LIGO event. But the later data suggests that what we were perhaps seeing is just some light that kind of burbled out of the side of this explosion. It wasn't jetted right toward us. And indeed, the energetics suggest that. This wasn't as bright as it would have been if it were that close and a jet directly pointed at us. Okay? So in a nutshell, this is one of the most challenging things about this event. This was not a normal short duration gamma ray burst by any means. And trying to understand this connection of what we've actually learned is a little bit tricky in terms especially of predicting what's going to happen in the future.
Excuse me, how would you actually explain this X-ray delay in terms of a different pointing? It was not pointed to us. What happened? Did it precessed or what?
Oh yeah, so that's a great question. So why would you expect, so if a jet's not directly pointed at you, why do you expect to see that jet at a later time? And so it has to do with the deceleration of the material in the jet. So initially it's a very high Lorentz factor, so you're only able to see 1 over gamma of an angle of that jet. And on a timescale of a few days, the Lorentz factor declines enough that the visible angle due to beaming comes into your line of sight. And so suddenly you see the rise and subsequent decline of the light curve. So that's the sort of unusual thing that happens here because these are such highly relativistic explosions. Okay. Okay, so that happened. So this looks like it's certainly a merger of compact objects. There was something that looked like a short duration gamma ray burst that happened at the same time, but it's not like any of the short duration gamma bursts we've seen in the past, which admittedly are a few, a dozen, 2 dozen, that are well studied like this. Okay, so let me ask the question, what have we learned? And I'll give sort of a negative, depressing statement about this. So we've learned that one gravitational event has an electromagnetic counterpart. Okay, that's very clear. And it looks like it's probably an off-axis short duration gamma ray burst. Okay? That's even a hard statement to make decisively. It was a short pulse of gamma rays, but it didn't have a hard spectrum like typical short duration gamma ray bursts. We have no other examples of short duration gamma ray bursts that have this luminosity or this kind of spectrum. So if it was a short duration gamma ray burst, it's nothing like anyone we've seen before. So it's very hard to make a statement based on the population of short duration gamma ray bursts about what we'd expect for the future. Okay. Another obvious thing that we know in gamma ray burst land is that long duration gamma ray bursts tend to look like short duration gamma ray bursts. If you just take like the first second or two of the emission, it's very hard, it's very time variable. So if you were to observe a long duration gamma ray burst way off to the side, it might look like this. You know, it's totally uncharted territory for what happens on when you're away from the center of the jet. Okay, so it leads to these 2 big questions that are very hard to guess and really can only be answered with continued observations over the next couple of years to detect more events like this. So how many of these do we expect in the future? Will we be detecting more gravitational wave events? And what we glean from that? So what really are the progenitors of short duration gamma ray bursts? How many of them are actually merger events? And can we relate that back to the production of compact objects in the universe? Okay, so that's really kind of where we're going in this field. And to do it, we have to exploit this new window, this new gravitational window, by utilizing ground-based resources. Okay? And at ASU, we have a lot of access to big telescopes. List a few here. But my focus has been more on the larger telescopes, and particularly collaboration with folks here using things in San Pedro. Okay, so I want to connect that up, and particularly RATIR, DOTI, and Katli. Okay, so I'll go through a few pictures of those. You can always ask Alan and others more if you want to learn more details about the particular telescopes. I want to spend a little time on RATIR because I also want to advertise a pipeline that I've written, and I'd like more of you to use to try to get more out of RATIR. Okay, so these are all robotic telescopes. They're all up there on San Pedro staring at that sky. And what we're trying to do is get them responding and coordinating to follow up these kind of explosions, to follow up large parts of the sky like that, and then to be able to focus in on very narrow parts of the sky to do the chasing. Okay, and that's kind of what I'm here to discuss with others, is how to make that happen. This is RATIR, right? So RATIR is the 6-channel imager shown there in the 1.5 meter dome. We've been working on this for nearly 10 years now, and it was online in fall of 2012. This is a picture of what RATIR is designed to do. So these are our 6 channels, cameras 0 through 3 doing R band, I band, Z band, Y band, J band, and H band. This is a series of pictures of a redshift 6 gamma ray burst. And so RATIR's job is to find the dropout. So if you follow the arrow there, the source is present in all these images, and it's not there in R band. So that's the signature of a very high redshift gamma ray burst. RATIR tries to make this detection in tens of minutes so that we can follow it up with very large aperture telescopes. Yeah, so that's basically RATIR's job, but that's not what I'll be talking about using it here today for. This is what RATIR looks like, and I just wanted to throw this up for one brief advertisement, and that's that we're working to add potential polarization capability to RATIR. So David Heriart is looking at polarization instruments that can go in with the optical cameras in this part of the instrument. And we're also potentially looking at polarization instruments that can go down into the infrared portion of the instrument. Okay, so that's new, something potentially to look forward to. Okay, so how do we do gravitational wave follow-up with RATIR? So RATIR is this what I'll call one of the bigger but narrow field instruments. And so RATIR follows the strategy of chasing only the bright galaxies that exist in one of these several hundred degree air regions. Okay, the process was written up by my student Zach. What we do is we target those galaxies based on existing catalogs, and we utilize the fact that we have all these channels to drive down any kind of false alarm rate that we would otherwise have in a single exposure on the fields. So what he goes to in this paper is how you can do image subtraction. There's always some bad subtractions that happen and keep you from being able to save out all the images you've observed of, say, a few hundred potential galaxies you're trying to measure. But what you can do is you can combine the different bands. Here he's combined R and I band, and you can drive up your image retention rate and drive down your bad subtraction rate so that you get kind of quality image reductions, and you get an overall false alarm rate that's very low and a fairly high efficiency. So you can expect to get images for something like 80% of all the galaxies you've observed with a very low false alarm rate, very low rate of intermediaries or things that are just chance fluctuations or images, because you have 2 to 6 images to look at. So RATIR's advantage is that we can point at all these galaxies, find a potential source, and then be able to say with very high confidence that what we have isn't just a noise fluctuation. Okay, so that's something that's sort of a different tweak on why multiple channels are interesting. Okay, and so that's what we do with RATIR. We've also been doing some neat work with RATIR on this question of jetting, and I wanted to advertise this for another student of mine, Robert, who's been working with folks here. So one of the ways you measure jetting, this is what the previous question got at, is you wait until the Lorentz factor is decreased enough that you see the effects of the jet. Okay, and what that does to a light curve, this is flux versus time. This is the 6-channel RATIR light curve for a burst called 160625b. which was the subject of a Nature paper because of some other observations due to polarization. But for us, the interesting thing about RATIR, this is the light curve. And the interesting signature in the light curve is this decline and then steepening that happens at a time of about 10 days. I've called it jet break right there. Okay? That time is the time at which the edge of the jet is comparable to 1 over gamma of the outflow. So the outflow has decelerated enough that the observer can see the edge of the jet, and so there's no longer material beyond the edge of the jet to keep the flux high. So the effect is that the light curve drops suddenly. And it drops achromatically, so it drops in all the RATIR bands and it drops in the X-ray band from Swift. Okay. In this case, this is a classical way of measuring the jetting of gamma ray bursts. It was a method that was evolved in the early 2000s. It was expected that this would be kind of bread and butter science for Swift. Swift would come along, measure hundreds of X-ray afterglows, and we'd suddenly know the whole distribution of GRB jets and what they look like. But it turned out that Swift and in general X-ray afterglows are much more complicated than we had thought. They have flares, they have plateaus, they have all kinds of variability. And it's next to impossible to get a clean measurement of jets for any significant number of gamma ray bursts using Swift. Okay? And so what RATIR did here is it did a very late time observation, kind of like what had been done in the area before Swift when people were still able to point Keck and very large aperture telescopes at gamma ray bursts. They would burn all kinds of time to measure these signatures. And these are happening at late time after the X-rays were complicated. So it's a time when everything is pretty simple. And the neat thing about RATIR is a big enough aperture and it has a significant amount of time that it can dedicate to this problem, that it can spend days to capture this kind of quality data. Okay, this is a kind of neat thing about RATIR that no other telescope in the world can do. Okay, and in this case, what we found is a very narrow jet, just a few degrees. This is sort of the extreme of the possible jets of gamma ray bursts. If all jets were very narrow like this, there'd be a whole lot that you're missing because they're outside of your range of view. Okay? We think typically short duration gamma ray bursts are about 10 times larger in their jet angles. Okay? But it's still a crucial unknown. What is the distribution of the jets of gamma ray bursts, and what do they tell us about the predicted rates of short duration gamma ray bursts that lead to compact object mergers? That rate is uncertain by a factor of 10, and sort of best case, it's an event rate of about 1 a year. So based on the GRB physics, we only expect to get about 1 merger event a year. Now, if a burst like this also has emission that comes out of the sides of the jet, that's very interesting because that could potentially allow closer events that don't have to be pointed to us to also produce gravitational waves. So that's a mechanism, if we can understand it, that would lead to much higher, potentially higher rates of mergers, or at least gravitational wave signatures where we also see a gamma ray burst because they're nearby. Okay? So this is some of the uncertainty. Another cool thing about this event is it also had a sort of a hint, a bit of a signature, that there is some interesting stuff happening out toward the edge of the jet that's kind of related to this question of what happens on the outside. And that is this little bump that happens right here that we captured in really good detail. If you look, there's a light curve declining, there's a little bump, and then it declines faster. Here I've normalized the light curve to let you see the bump a little better. See how there's just a little bit of a bump up by about 10%, 10 or 20% that happens at the time that we're seeing the edge of that jet. So it sort of suggests that there's extra emission or extra emissivity happening on the edge of the jet. Here's a picture of that. If you plotted it versus angle or the 1 over gamma that you're seeing, it's kind of like the edge of the jet just gets brighter for a little bit. So it's at least consistent with this notion that the emission in the jet isn't just in this cone, but there's potential stuff that you see off the line of your line of sight. Okay? So this is a whole area that I think has just been not well pursued during the entire last decade of Swift, and it's very important suddenly in trying to understand how many gravitational wave events we're seeing. And hopefully in the next year or so, we'll sort that out. Okay, let me advertise a couple of things. The way we run these telescopes is fully automated, and my job has been to write some of the software. And what I want to do is expose more of that software to you so that you can use it for RATIR reductions. This is an example web page generated for RATIR in the case of a gamma ray burst. So for a gamma ray burst, the telescope slews within a few minutes, typically, interrupting whatever it was going on. It starts capturing data. And then the pipeline's job is to reduce all those data, co-align them, photometer them, compare them to catalogs, and identify new sources. Build light curves for all the existing sources and build light curves for the new sources. Okay, so there are many, many knobs that can happen in there, but the point is this is fully automated. It's been running for 5 or 6 years now. It's very stable, and it can be applied to other sources than just gamma ray bursts. Okay. It also, for us, gives us basically all the way, takes us all the way to the science. So RATIR starts taking data, starts producing images, the pipeline starts reducing them, and then it even generates the couple of paragraphs that are what we send out to the world. So typically our interaction is to log in, copy and paste those paragraphs, and that's our science until we sit down and write papers. Okay, but this is totally automated, no people involved in this stuff. This is what has to happen for gamma ray bursts because it's so fast.
What's the time scale?
So for things to happen,
Yes.
so the gamma ray burst happens in 10 seconds. RATIR's typical fast responses are a few minutes. We're typically reducing data, and the next 10 minutes, the first results are coming out, and then the final results are within a half an hour. We typically observe for another hour or two. So we either do this within 10 minutes of the gamma ray burst, or we wake up the next morning and we send this result out. Okay, so that was RATIR. One of the things I'm also hoping to discuss a lot more is how we can connect up the other robotic telescopes that are on San Pedro amongst each other and with RATIR, and talk about Dottie and Coatli. So there are various sizes of telescopes up there that are robotic and automated and also tied into this reduction software. And so we'd ideally like to have those working with each other, able to respond to these triggers, respond to programming and cues from the general community, and then also to be able to interact to get work done in efficient manners. Okay. This is a couple of the images that came from Dottie. So Alan's probably showed you this before, but there's the full moon in the top right. This is 2 images, about 20 minutes exposure in 2 of the cameras. You can see how there's kind of 2 squares there. Each field is a few degrees by a few degrees. Eventually, Dottie, in a few months, will have 6 telescopes. So it'll have a 10 by 10 square degree field, and it will be 3 times larger than this. So for gravitational wave science, Dottie is very exciting because it's the instrument that can observe the entire air region in the course of a night, allowing us to see the galaxies and then everything between the galaxies, depending on exposure time to depths of, say, 17th to 19th magnitude. Maybe a little deeper if we find really exciting things. Okay, and so for example, Dottie could find a bunch of candidates, but then we need the smaller aperture, larger aperture telescopes to then point at those candidates to try to find out if they're interesting and they're varying. So this is a way that would be interesting to connect other telescopes to Dottie. Okay, it's just a picture of the facility. They're using these little off-the-shelf telescopes and cameras. Here's an example of one of the reduction pages for Dottie. Okay, so what I do is I take the images from each camera and I generate a separate web page. This is an example of the stack for those 20 minutes of observations. There's a bunch of stars there. There's some galaxies. What I do is I compare that to existing catalog and I find everything that's new. So if anyone can see it, there's one source right there called number 1, which was the only new source out of the 35,000 sources in that one frame. Anyone guess what that is? It's kind of impossible to see here. It ended up being 2 satellite trails that crossed during the course of the observation. So stuff like that happens, you get false alarms, and it's pretty trivial just to look at this case and figure out that it's a false alarm. But in general, some of the things you might get are more subtle, and it would be interesting to have some of the other telescopes following those up to figure out if they're true variable sources. Okay. But the cool thing about this pipeline is that it's able to generate light curves for all those sources, to do this quite fast in a way that keeps up with the data as it's coming in, and then to generate these summary pages that'll then feed on to our reporting of the results and hopefully our collaboration within the different telescopes. Okay. Okay, the other telescope I want to mention is Katli here. So Katli, so if Dottie was a 11-inch telescope, 6 11-inch telescopes, Katli is a half-meter telescope with better seeing. It has a sensitivity that can in principle approach that of RATIR in the good seeing cases, but it's an optical telescope, so it doesn't have the infrared capabilities. It's able to point to more parts of the sky than RATIR can, and it's able to slew very fast. So it's a really interesting facility to think about this hybrid approach of looking at galaxies or looking in between galaxies, and to be able to combine the follow-up approach from the different telescopes to use something like this to go after what's really exciting. And this is what the Katli Pipeline, so you can see how this looks like what I just showed you in a few slides ago. So I've kind of developed a very similar pipeline for Katli that we've started using for identifying sources. So here, everything in blue is a known source in the USNO catalog, and red are unknown sources, which are basically just a little fainter than what was present in USNO. So Katli is able to go deeper than we were with Dottie. And what I do is I generate light curves and other things for all those sources. So in one of these images, you can click on the circle, you get a light curve. I'm also working on things like some of the buttons on the top. You can press it and it'll show you a DSS image. So you can blink against your captured image. We're doing image subtraction, so you can blink against the first half data, the second half of the data. And if I could click on the button, there's a little yellow region that's hard to see here, but there's actually a gamma ray burst right there. You can click on that and you can see a light curve and write up a GCN and stuff. So again, it's fully automated. We're trying to work to incorporate some fancier reduction techniques, but to keep everything running very fast so that we have an interface here that generates a list of new and exciting sources that we can write about or pass on to other telescopes for continued analysis. Okay. And just to advertise Colibri. Colibri is this thing coming up. I'm also trying to write a pipeline using the same tools for Colibri to focus on gamma ray bursts, but potentially also more because it'll be a wider field of view instrument. Okay. Let me finish with a little bit of thinking about looking forward. So I've focused on gravitational wave sources, but in 3 to 4 years, we'll also have the LSST to worry about. So this is the LSST plotted in the background, Large Synoptic Survey Telescope. And all the thinking about the LSST suggests that we're moving into a very different regime for doing astronomy. Okay, so for example, LIGO will be detecting sources, and in a given night, we expect something like 100,000 uncatalogued new transients. Okay, so to do anything with that data set, so it's sort of taking where we are now, where we're finding maybe an interesting source in night, or some of these surveys are building them up, and we're trying to work out these methods of automatically following up sources. One of the reasons we're doing that is because we're trying to build toward this regime where we could do even a little bit with 100,000 sources coming in a night. So even if we could follow up 100 of those, maybe the brightest ones, that'd be very interesting. But to do that, to approach this regime, we need our facilities to be totally automated. There's no room for people to command and control and schedule. And we need them working with each other, which is a totally novel thing in astronomy. Telescopes need to sort of schedule each other and prioritize in order to do any kind of science in real time with a data stream like this. Okay. So this is, I think, super exciting. It's where things are going. And I'm getting a bit alarmed because it's going to be there pretty fast. So we don't have a lot of years, maybe 5 years before we're solidly in this regime. Okay, but I think it's the time now to be thinking about how best we're using our robotic telescopes and what we're working toward. Okay, that's it. Thank you.
Questions? Here. The determination of redshifts is crucial for understanding GRBs, for using as cosmological probes. So as far as I know, the main ways to determine redshift is associating with the host galaxy or when you have absorption spectra. And the method that you are now, the dropouts, what's the expectation? What's the main problems with this method, and what's the expectation of that you have for inferring redshifts for GRBs?
Yeah, so spectroscopic redshifts give you redshifts to precision of 1% or a bunch better. You get very accurate measurements of redshift. Photometric redshifts, like this dropout technique, give you redshift to 10% or so. So it's, at least at the start, even a cruder measure of distance. But the dropout technique is just a very efficient way of finding distant objects, right? We're designed to get dropouts out beyond redshift 5 or 6. If you had some nearer channels, you could push that to more nearby cases. But it's a regime where the sources are so faint, you can't afford spectroscopy. They're much too faint for that. You can't prioritize the time until you know they're that distant. So it's a good method for rapidly, efficiently identifying a distant source that you'll then go observe with a proper spectrograph.
And how many already were detected with the redshift for these objects? You mentioned one, yeah? That was the...
So Swift finds, it's about 5% of the Swift sample. Swift finds about 1 a year, so it's very rare, 1 to 2 a year. And we typically find 1 or 2 a year. We're pretty matched to that level if you start with redshift 5 or beyond. It's not super common science, but we only know of 3 or 4 of these in the last decade. So finding 1 is a very important result. And the few that we have found are significant for that reason.
And the record is redshift 6, or there is, I think
there's redshift 7 now.
7, yeah.
Yeah.
I wanted to ask you about the bump and how do you know that it's the edge, what you call the edge of the jet? Or
it doesn't have to
the
be.
other possibility is that it's just a discontinuity. Most jets in all the sources are discontinuous.
Mm-hmm.
They're not continuous jets.
Yeah.
So how do you know that it's the edge?
So let me give you a bad argument first. And that's that it happens at the same time where we are seeing the edge of the jet, or at least seeing the effect of the break, which is roughly the time where the surface of the jet is coming into causal contact across the whole thing because of the Lorentz factors. And so it's kind of the natural time where something like that happens. Things like clumpiness or differences in the variation of the size, of the brightness of the jet tend to produce very broad temporal features because you see them not just for the time they went off, but for a much longer time. So this doesn't really work with that picture. And it's not super clear that it works with what happens at the edge of the jet. It's just that there's a feature that seems to happen at that same time. And so it's suggestive that what happens is some emission that's just happening at that time. So not just spatially at the edge of the jet, but also is also lighting up at that time. And this black here was a model we came up with to do that. And what that model has to do is it has to invoke some edges of the jet that are bright. That could be clumps or that could be emissivity. But it also has to make that flash for a delta second, delta function. So it's very hard. It could be something else, but then why does it have to be simultaneous with that jet? Yeah.
More questions? So I have a question, but probably it's a very...
So what's the plan with Doti, Katli, and RATIR? So Doti is going to be looking at the whole sky. It finds the GRB. It tells Katli to focus in that part, and then RATIR will see the infrared afterglow, or how's it going to work?
Yeah, so we were just talking about this just starting today. We're starting to go on the whiteboard, and we're trying to draw out all these possibilities. So Dottie can observe the whole sky. So we're going to do that no matter what, because we might want to look back at that data set even if someone tells us later there's something interesting. What we'd like to be able to do is conduct a narrow field survey with RATIR and possibly Dottie. So RATIR gives the infrared, Katli. Katli gives more field of view coverage, but only optical. And the new part of this that I'd like to look at is being able to find interesting stuff in Dottie and then also have Katli chase those, because Katli can point so fast, whereas RATIR's sort of slow to the game in that sense. So it's a large parameter space of potential things we can do, and we're trying to draw out the different possibilities and figure out how to do it. Yeah. We still have a break because the next runs haven't started yet, and when they do, they're going to go public. So we want to be ready for that.
More questions?
Yeah.
Go ahead.
So I know you say the rates are difficult, but around how many?
So
Neutron star does LIGO say we're going to have?
So if you start with the gamma ray burst, which is sort of the most natural way to start for the predictions, the key uncertainty is the jetting, right? So you have a gamma ray burst rate. You can take that. You can try to map it back to low redshift, where we've never seen a short duration gamma ray burst before this event, but we see them at typically redshift 1/2 or beyond. So if we extrapolate those rates back and do some guesses for jetting, we expect something like 1 LIGO event in the LIGO volume, a couple hundred megaparsecs per year, plus or minus 10. You know, it could be a few, it could be 0. So there's a huge uncertainty on it. If there's this new channel that can allow events in the nearby universe to emit gamma rays when they're not pointed at us, that can bump up rates, but we still don't have a very good way of predicting those rates from the existing catalogs because we don't have examples of those in the gamma ray burst catalog. So there is a really interesting paper that came out from the Garlanda group that predicted the gravitational wave event should be dominated by these off-axis nearby events before this event happens. I think that's kind of cool. That may or may not be truth because we still have just one event that's all based on now. So I would say that the sort of whole field is very much open. I would guess that we are not going to see a lot of very easy nearby events like this, where we're going to get the very challenging, very large area events that we'll really need Dottie to chase after, and it's going to be difficult. So I think we were very lucky to get a very clean event last year, around the time that LIGO was stopping its run.
One question and after.
I'm not familiar with the science of LSST. So could you briefly explain or comment why is it that it will capture so many events per night, or was it per year?
Per night, it's like 100,000 per night. So Large Synoptic Survey Telescope is a telescope that's under construction now in Chile. It's very, very huge étendue, so large area sky coverage. So it's able to monitor effectively the night sky per night. So you're basically taking very deep images of the entire night sky in multiple bands at a level that just hasn't been observed in the past. So like I showed you the Katli image, there were all those new sources that weren't in the catalog just because I went a little deeper. LSST is going to be observing the variable night sky, but also a little deeper, and it's just probing a whole new parameter space. And it's just producing a massive number of images, looking for things like near-Earth asteroids, looking for variable objects like supernovae, looking for gamma ray bursts that aren't pointed to us because you can still detect them in the optical if you wait a few days. All sorts of new things that people are trying to do with LSST, but it's a data stream like nothing we've ever seen before. It'll be petabytes of images and this tremendously rapid rate of discovery.
I have two questions.
Yeah.
It was my understanding that LIGO had several other events that they have not worked out yet, not as spectacular as the August 17 or whatever it was the date.
That might be true.
I don't know. They were not caught up by GRBs, or what happened to those? That's one question. And then the other comment, if you mention Katli might get to magnitude 17, LSST, which magnitude would it reach, 25?
Yeah, so it's going quite a lot deeper. You have to integrate for a while to get to 25, but most of their sources will be far, far fainter than 17. Yeah. So the first question about other things that LIGO saw. So LIGO, I showed this on a plot maybe at the very beginning. These are at least the ones that were, well, they thought they were real events from LIGO where they were very confident, and they sent out, they sent out notices to the community. And there's so far been 5 or 6 of those events. There we go, this plot. So these are the ones that, as someone who was following LIGO triggers, if you had the agreement signed with them, you could follow these 1, 2, 3, 4, 5 different events that they reported, which were for them very highly significant results, very low false alarm rates. They may have fainter events they haven't released yet, I don't know. Only one of these, aside from the GW event in the corner, had a potential gamma ray burst. And this was an event that had a very large error region, and Fermi GBM also had a very large error region, but there was an overlap where there was a pulse of gamma rays. So it was a possible counterpart, but everything else doesn't have any optical counterpart.
Okay, more questions? Can I make my question? So are you working on the other way around? I mean, in the sense that LIGO emits some alert that telescope should detect some GRBs or something, but are you working on the other way around, that you detect that GRB and then look into the data in LIGO or Virgo, and then try to see whether there was some event?
Yes, I worked on that angle of the problem back in grad school, because LIGO's been up and running for a while. When I worked on the Heti 2 satellite, we had gamma ray bursts from Heti 2 that we would go back and search through in the LIGO data. These LIGO runs were organized very differently from that approach. Their approach was to get the instrument nailed down, understand their data stream so well that they could produce an alert that they trusted very accurately. And they wanted to get everyone else outside of that game. So they're just giving you an alert, and then we would feed back and tell them whether we found something or not. So I wouldn't be surprised if people start, I'm sure all along, if someone finds a gamma ray burst, they look back at their data. That's been happening all along. But it wasn't the path for discovery in this case.
Yeah, but people is working on that
Yeah,
direction. Yeah. Okay, so that's interesting. And if there is not another question, I have a last question. So, what other kinds of science we can do with RATIR and all? For example, for you, the garbage.
What was the second part?
So, what is the other science that we can do with RATIR, Katli, and all that? So, I mean, you are interested in GRBs, but you also observe galaxies, stars, and all
galaxies,
that. So, what we can do?
I know people are interested in quasars and variabilities. You have the time domain, which is opening up as a new axis for understanding sources like that. Stars and exoplanets. I think thinking in terms of variability, particularly for redder objects, is really interesting. There's all kinds of stuff that folks can do, and I hope that the pipeline I've written is generic enough that it could be used for most sciences. The only one kind of science I've had trouble with in the past is doing like supernova observations when you have a big galaxy and you're trying to do sky estimation. So Ori Fox to some level has helped solve that problem, but for most sources, I think the pipeline is pretty good. And so we'd have to play it by ear. If you have really defocused images and you want to do a very precise photometry, you have to see how it works for that. They're just case-by-case things we'd have to look at.
Okay. If there are no more questions, let's thank again Nathan. And we have after parties.
You are invited to it, so